Welcome to the class of Digital Signal Processing. In this video, we are going to learn Fourier transform and the frequency analysis of signals. This lecture contains two parts: the frequency analysis of continuous time signals and the frequency analysis of discrete time signals. Continuous time signal is signal xt as a function of time, continuous time t. Discrete time signal is signal xn, that is a function of integer index n, is the time index. For each part, we will discuss the Fourier series of periodic signal and the Fourier transform of aperiodic signals. Then we will discuss the relationship between the Fourier transform and its general form, the Z transform. Then we will touch base on the frequency domain classification of signals, the bandwidth concept. For example, I can decompose a periodic signal that is square wave into a sum of weighted sine functions, and it can be a sine and a cosine functions combined. So let me using a sine as an example. C sub k are the weights. These sine functions are harmonically related, meaning that the frequency is given by k f0, where k is integer, 0, positive, negative 1, positive, negative 2. f0 is the fundamental frequency, that is the inverse of signal period, which is, in this case, for the square wave that is from this rising edge to the next rising edge. So if we're looking at a signal from the frequency domain, it's as if we are only counting non-zero values on those frequency pings, which at 0, f0, 2f0, 3f0, 4f0, so on and so forth. And these weights, c sub k's, can be any complex number. Let's look at the example demo for this square wave. So the square wave can be approximated by a sine function, which is sine theta, the function of theta on the top line. That's the red curve, which is sine wave, approximate the original square wave. If I'm adding another harmonic term, which is sine 3 theta, with amplitude only a third of the first term, then we're adding this green circle as a function of theta. Then the green curve is a much better approximation of the original square wave. I can add another harmonic sine 5 theta with a weight 1/5 of the original yellow wave. And that gives me the blue waveform that is even a better approximation of the original periodic square wave. I can add yet another sine function, that's another harmonic of sine 7 theta, with an amplitude only a 1/7 of the original sine wave. And then we get this red curve that approximates the original square wave. So we can imagine if I can add more and more of those harmonics, eventually this approximation will be ideal, that's aligned very well with the original square wave. Now we know a continuous time periodic signal with period t sub p can be represented as a linear combination of harmonics, which are those harmonically related exponentials. Exponential is a mathematical form to express cosine and sine functions. So in this case, we have this function xt, as long as it is periodic with a period t sub p, I can decompose as a sum of this weighted sum of all these cosine functions. Cosine and sine, those are the exponentials. Where here we know kf0, and f0 is the fundamental frequency, that is 1 over t sub p. It's here. On the other hand, all these complex weights, c sub k, can be calculated. We can calculate it using an integration. Integration of xt times this core. Now compare with this part, what we have here is e to the power negative j 2 pi kf0t. Because t is continuous variable, so we do an integration dt over one period, t sub p. And then we do a normalization over one t sub p here. That is to calculate all these complex coefficients, which are those weights c sub k here. The first equation is called a synthesis equation. Decompose any continuous periodic signal into a weighted sum. The second equation is called the analysis equation. That is to calculate all these weights, the frequency domain weights. We can think that as the first equation is we get all these frequency representations, and we want to calculate xt from frequency domain to time domain. The second equation is to calculate from my original time domain signal to find c sub k's, where c sub k's represent the measurement of frequency domain. So we have an equation, analysis equation is transform a signal in the time domain to a signal in the frequency domain. And in this case, my frequency domain signal is discretized as c sub k, as again, those are those discrete values on the integer multiplier of f zeros. So these are the c sub k's. Okay. Originally, when Fourier invented the Fourier series expansion, it uses components as cosine and sines. So everything is in the real coefficients. We can write any continuous time periodic signal in a sum like this. This is a combination. So these are a combination of cosine and sines with all these harmonics. It's kf0, and here is kf0. Those are the harmonics. And the coefficient a sub k, b sub k, a sub 0 is directly related with the coefficient c sub k's that we developed in the previous page. Because we are dealing with complex exponentials, here is just real numbers, cosine and sines. A's and b's can be directly related with coefficient c sub k's. And in this case, we using a polar form to indicate this is the value, the amplitude of c sub k, and the theta k is the phase of c sub k, and then we can write out these relations to find coefficients a's and b's. Mathematically, exponential is much easier to deal with. So from now on, we will using the exponential as the call for the Fourier series expansion. Before doing the Fourier series expansion for continuous time periodic signals, there is a precondition that needs to be satisfied. It is called the Dirichlet conditions. Guarantee that xt and its Fourier series represent are equal at any value of t, which means the Fourier series expansion can be written. So the conditions have three parts. First is xt has a finite number of discontinuities in any period. So in practice, a practical signal should satisfy that. Second condition is xt contains a finite number of maximum and minimum during any period. So again, for a practical signal, during any finite period, we should have a finite number of maximum and a minimum. So in practice, this condition should also be satisfied. And thirdly, that xt is absolutely integrable in any period. That is, absolute value of xt, we integrate it over one period, is finite. Again, that is satisfied by any practical systems. So for signals, for these Dirichlet conditions to not satisfy, and it will have some theoretical signals. So we need to be careful before we do any Fourier series expansion of Fourier transform that we need to check with this condition. Now let's look at the power density spectrum of a periodic signal. So using the tool that we have, which is the identity equation for the Fourier series expansion. the power of a signal, xt, absolute value square, if xt can be any complex value, so this is given by xt times xt conjugate. And we call that instantaneous power on time instant t. That's the instantaneous power of the signal. Therefore, to calculate the power of a signal, what we do is we are going to integrate this instantaneous power over one period, dt. So that is the energy of a signal over one period, t sub p. Divide by the time span, and we got the average power of the signal. It's a periodic signal, so this average is across the entire signal. Then we are using the equation, which is the synthesis equation, and work that on x conjugate. So x conjugate becomes a weighted sum because it's conjugated. So we have c sub k conjugate times e to the negative power negative j 2 pi kf0t. So in this line, we are doing a summation, and then the outer is an integration, and we find the result. Because both summation and integration are linear operation, we can swap their order, doing an integration first and then doing the summation. Simply we're moving the summation to the outside of this bracket and moving the integration to the inside. So we do integration first, xt times this e to the power negative j 2 pi kf naught t, the integrate dt. These are the function of t. So integrate dt over one signal period. We also bring this normalized term here inside the bracket. So this bracket here is our analysis equation. So that will give us exactly c sub k, this coefficient. Therefore, finally, we have this format. We have a sum of c sub k conjugate times c sub k, that is c sub k absolute value squared. So here, this also represents average power of the signal. So what we have here, all these c sub k absolute value square are this. We have a frequency domain, and these are the harmonics, f0, 2f0, 3f0, 0, negative f0, negative 2f0, negative 3f0. On all these harmonics, we got a c sub k absolute value square. Now, adding all these together, that gives me the average power of the signal. Therefore, the picture is going to show me the power density spectrum. So c sub k absolute value square, that's the density spectrum. Let's go from the periodic signal to an aperiodic signal. What we can do to make this change is first we make the period infinitely large. So Tp approaching infinity. My aperiodic signal is a periodic signal, a fictitious periodic signal, when this period approaching infinity. Okay? Because x sub p is a periodic signal, we can write as before using the Fourier series expansion. And then we find out c sub k using an analysis equation. It can be calculated like that. So we do an integration over one period. Here is from negative t sub p over 2 to positive t sub p over 2. And that will give me c sub k. Now here, because my period is infinity, therefore I can using the integration over the entire time axis from negative infinity to positive infinity, and writing this to find c sub k. And we define this part, integration part, as capital XF, capital XF. So now we know what we do for a aperiodic signal extension from the periodic signal. we did first, the period becomes infinitely large. Second, we need to deal with the f0. f0 is the fundamental frequency, so it's the inverse of t sub p. When t sub p approaching infinity, f0 approaching 0, it's a very small number. It is right here, this part. This is f0. It approaching 0. Well, however, if I put a 0 here, it's not going to show me anything. So I need to do something smart. Instead of doing 0, I can write this into a very small delta f. Right? It's a small step. As my step size becomes smaller and smaller, and eventually that will give me df. And the third part is here. We got a kf naught. Kf naught is those harmonic frequencies. Because f0 becomes smaller and smaller, I'm counting how many f0s I have using the counter k. When this becomes very small, eventually this will give me a continuous variable. Everything is connected, so I'm using a continuous variable, capital F, to represent, to replace kf naught. So this is the third part. With these three changes, now we can write, we define the kf naught, it becomes my continuous variable f, which is also k over t sub p. Delta f, defined as f naught, we know it's very small, and eventually we make that as a infinitesimally smaller number, df. Also, we have this period which become infinitely large. Therefore, my periodic signal, xp, can be written in this format, which is, we have 1 over t sub p times a sum, a weighted sum. Now remember that I have this weighted sum, that here, c sub k is already becomes this 1 over t sub p times xf. So writing the xf here, and then this is the synthetic equation. So we have called term e to the positive j 2 pi kf0t. Okay. So with this normalized term, we know that is our delta f. It is our delta f. An aperiodic signal, xt, is a limit when t sub p approaching infinity of x sub p. So we plug in this equation on the limit when delta f approaching 0. Therefore, I have here this term becomes xf, because I am using a continuous variable f to represent kf0 or k delta f. I'm using a continuous variable f to represent kf0, and I'm also using df to replace delta f. So eventually, this is what we have for the synthetic equation. So let me write out this again here. And the synthetic equation becomes xt equals to an integration xf times e to the power j2 pi ft dt. And this is the inverse transform, the inverse Fourier transform, because we have a signal, xf is a frequency domain signal. We want to find the time domain signal here, xt. So this is an inverse Fourier transform. The analysis equation is the definition of xf, which is given by this integration of xt times exponential e to the power negative j 2 pi ft dt. And this is the direct transform, which is the direct Fourier transform. We have a signal in the time domain. Using the Fourier transform, we want to find out the signal in the frequency domain. Next, we can use some similar steps to find the signal energy of the aperiodic signal. So xt, absolute value square, is the instantaneous power. Therefore, I integrate xt, absolute value square, over the entire time I got the signal energy. So the signal energy is in this format, where I am using the synthetic equation or the inverse Fourier transform to replace xt conjugate. So we got that. And due to the linearity of integration, I can swap the order inside and outside of integration. Therefore, the integration of dt first, and then the integration of df. So this part is my analysis equation, which gives me xf. So we have here, again, that's xf conjugate times xf integration df. Therefore, I got the final answer for the signal energy, which is integration of xf absolute value square df. So the signal energy can be represented as the integration done in the time domain or an integration in the frequency domain, which makes sense because once you measure the signal energy, whether in the time domain or frequency domain, that should give you the same number. They should give you the same value. And this relation is called a Parsevals relation, such that I have a Fourier transform pair xt and xf. This is the Fourier transform pair, and it will satisfy this Parsevals relation. These two integrations, absolute value square integration, will be the same. Now we know for an aperiodic signal, xf absolute value square can also represent its spectrum. That's the density spectrum. So we have all these frequency here, which is continuous. And then I have these are the xf absolute value squares, non-negative number. If I sum all these together across the entire frequency, that will give me the signal energy. So this function, xf absolute value square, the function of f, that gives me the energy density spectrum. We define that as capital S sub xx as a function of f. Those are the energy density spectrum, or just called a spectrum. If signal xt is real, given the Fourier transform equation, xf equals to integration of xt e to the power negative j 2 pi f t dt. Then we find out the absolute value of x is even symmetric, and the face of x, capital X, is odd symmetric. It follows that my spectrum density will have this. It's also even symmetric. So like this picture, the spectrum density is always even symmetric, which means we do have negative frequency, we have positive frequency, we have negative frequency. Now the negative frequency is mathematical artifacts that are coming from the core here when we do the Fourier transform, because we are using the exponential instead of real cosine and sines.